Good afternoon, everyone. Today I have the great pleasure to welcome Professor Guillaume Galliero. Professor Galliero received his master's degree in fluid mechanics at the Bordeaux University, where he also completed his PhD in mechanics. Much of his work is devoted to study fluid mechanics, from the physical chemistry of interfaces to the geology of reservoirs, also including the thermodynamics of pressurized fluids, geomechanics, and geophysics. Professor Galliero is currently a professor at University of Paris de Pays de la Dour and head of the Laboratory of Complex Fluids and their Reservoirs. He is also chairman, member of the organizing committee of 5 international conferences, and member of another 10 scientific committees. He has over 90 publications in peer-reviewed journals, more than 80 publications in international conferences, and he also collaborates with more than 15 different laboratories around the world. So once again, welcome, Professor Galliero. Thank you so much for being here, and please feel free to share your screen and start your presentation.
Thank you, Yamara, for this really kind of introduction. I'm not sure that I'm working on all that subject, but still. And thank you, Fred, and your team for inviting me. It's a real pleasure to be among you. It's among all these prestigious speakers. So I will try to share my screen. So up, this one should be the right one. Is it okay in terms of screen?
Okay.
Okay, everyone is seeing it?
Yes.
So perfect. Try some words about Pau, because it's quite a small town. It's located in the very southwest of France, and it's a university where there is something like 15,000 students, and it's nice because it's close to the sea and close to the mountain. So if you like all that, it's a really nice place. And I'm heading a lab where we are trying to do all these things. And so from the physical chemistry to the geology. And so the philosophy, the strategy of our lab, it's a kind of a bottom-up approach, but most often it's a top-down strategy where I try to understand what is going on at small scales. This is something I will focus during this presentation, to go to time in scales, and at the end, to better understand what is going on underground and how to store energy, how to produce georesources. So in this lab, you have about 120 members. Some are chemical physicists. I would say that I am a chemical engineer. We do have as well geomechanicists, geophysicists, and geology. So first, the motivation of this work, it's mostly to improve the management of georesources and as well to the underground storage, because it's clearly a crucial point for having a good energy mix. And so I will deal with topics which are related to better understand the fluid origin and migration underground, how they move, how they migrate, how they fractionate underground in a porous structure. I will deal as well about the initial state. So you have a reservoir, you have fluid in them, and how we could use this molecular simulation to better understand how the fluid organize themselves in such a structure. And I will discuss as well topics related to gas storage, and especially how to monitor that. So if you are thinking to all this problem, okay, there is a rock structure, there is porous medium, but there are fluid in it. And so it's crucial to understand exactly how fluid behaves in such a underground condition. So when you are looking to these properties, they are present at all stages of georesources management. When you are dealing with geophysics, to locate, geochemistry, to trace, when you are storing, when you are producing, even processing or transformation. So they are everywhere. And you still have, you have a lot of tools which are available. Most of you know them well, but they're often limited when you are tackling a new system, which means that overall, even if there are a lot of available data, I think that there's still a need for data and maybe more physically based models. They are still required. But the problem is that when you are dealing with georesources, conditions are harsh, and so the experiments are sometimes difficult to achieve because of high pressure, because of EHS trouble. So how we are trying to deal with that, or at least to tackle some parts of that. So we are using molecular simulation. So most of you know that well. So here it's something adapted from Cascabin. So where you see time and length scale, and depending on the time and length scale, you may choose different simulation tool, going from the ab initio simulation for very small system and very short time to continuous approaches to deal with the reservoir itself or even the basin. And when you're looking at intermediate systems, so when you are interested in interfaces, porous structure, I would say that atomistic approaches is a nice tool, and you can have as well mesoscale. So I will deal mostly with these two kind of tools, numerical tool to tackle that problem. And when you choose one tool, for sure, your choice is guided by what you are looking after. Even if you can couple the different scale, I will say some words about that. So even if I think that most of you are really well aware of what are molecular simulation, it's, I think, a quite powerful tool because you start from a description of the matter simply by molecular models, typically force field. Then you are doing this molecular dynamics or Monte Carlo, and you obtain exact emerging properties, exact for your choice in terms of force field. And how could you use that? I think in two perspectives, both to develop, to improve model theories, or in some situation, even to provide pseudo-experimental data. And this is something that I will try to show you during this presentation. So our strategy is the following. So we are trying to develop, or sometimes to use, simulation codes to study, or even sometimes to model, as finely as possible, fluid properties in terms of, or as well, behavior and transport. So we are trying to better model properties themselves. So it's, for instance, some scaling law in terms of interfacial tension, where you can show that all interfacial tension may fall on the master curve. There is something related to the excess entropy scaling, where you try to define in the supercritical region a gas-like behavior and a liquid-like behavior. We are trying as well to use this tool to better understand the physical mechanism. So in terms of transport of matter, so when you have two fluids that are mixing with each other in a porous structure, how they move under forces and external forces. Here it's another case that I will detail a little bit in terms of transportation of gases through complex amorphous structure, topics that UNIs know well. And sometimes we are trying to upscale this information. And to do that, there is basically two strategies. The first one is to couple this molecular simulation tool directly with continuum approaches by an exchange zone. So you couple small scale, molecular scale with the continuum scale simulation. And in some other, as I will show later, you can even upscale directly the result from the simulation at a smaller scale, at the molecular scale. So again, the idea is to provide an overview of some results. So it will be like some snapshots on some results that we did obtain during the last year. So I will start from what I have called the nanofluidics. So it's simply fluid mechanics at a nanoscale. And why is it an interesting topic? It's because in such situation, the surface effect becomes dominant over the volumic one. So you have that when you are dealing with geoscience, georesources in cap rocks, in shale, or even at surface when you are dealing with membrane. So in most situations, when you are dealing with such system, the usual continuum approach should be revisited. to provide you some insight about that, here I have shown, a small droplet confined between two solid walls, and the colors correspond to the variable density in space. So as you can see, there is a strong structure in the liquid phase, and there is such structure has an impact on the behavior of the fluid itself. So, but the problem is it's relatively difficult to perform experiment at that scale, even if you look, for instance, to results that were provided by a surface force apparatus, this structure could be inferred from the solvation force versus the distance between two plates that could be measured. And so an option to better understand this situation is to employ this in silico experiment using this molecular simulation. So here it's an example of a diphasic wet flow. So here you have two liquids that you share, and you look at the evolution of the interface between the two, and especially at this point, which is called the triple line or the contact line dynamics. So I will first start with some issues in simple system. So my case study is the following one. So I will look after the problem of multi-phase dynamics at the nanoscale. So I will deal with a simple nano droplet in a perfectly flat slit pore, which is fully rigid as well. So because of this fluid structure, strong structure, one can expect some physical phenomena to occur. For instance, because of these inhomogeneities in terms of density, we could expect some effect as well on the viscosity, a kind of local viscosity that depends with space. Because there is a frontier between a liquid and a gas, or two liquids, you may expect as well viscous stresses between the two phases. And when you are looking at the contact between the two fluid phase and the solid phase, one might expect some behavior related to the Young tension, especially in the dynamic regime. So often called the dynamic microscopic. I will not tackle all that problems, but I will just focus on two of them. The first one is how fluid inhomogeneities may have an impact on the dynamic properties itself. So this is something done with some colleagues from the LFCR, my lab, and François Montel from Total, so with Hairong. So the question is simply, is viscosity variable in space because of fluid heterogeneities, because of the confinement, or because of the proximity of a surface? If you see it in an integrated way, dynamic surface force apparatus has already shown that the effective viscosity in highly confined situation increase usually. And so the idea was simply to look at the simple fluid, Lennard-Jones-like, confined between two solid walls, and sharing such a structure to look at the response in terms of shear rate and shear stress. A brief picture of the fluid density profile. So again, strongly inhomogeneous. And now if we look at what is the viscosity in space, so here is a solid wall, here is a pore center because the system is symmetric. So I just show half of the system. The symbols correspond to the local viscosity computed from the simulation, the molecular simulation. And what you see immediately is that either you are at low pressure or at high pressure, viscosity is variable in space. And indeed it follows more or less density variation. But if you just deduce the viscosity, the local viscosity, taking into account the variation in terms of density, what is called a van der Waals model, you obtain the full line, which is qualitatively consistent with the molecular simulation result, but not quantitatively. And it's worse when you are dealing with high pressure situation, which means that there are non-local effects. And to tackle that, it's relatively simple. You can employ what we call the density functional theory. So just we assume that locally, the information here does not depend on the density at this point, but as well on the variation of density around that point. And so if you employ such a model, what you see immediately is that you can capture with such a model very well the variation of viscosity in space. So the main message are the following one: the fluid viscosity could be variable in space and is non-local. And this is interesting because it means that in some situations, the effective viscosity is not the bulk viscosity when you are dealing with fluid confined in such nanometric system. Now, a second point, always on the same problem, which is related to the viscous stress when you are crossing a fluid-field interface. So this is something done by with postdoc Peter Johansson in the lab, with a colleague from EMFC at Toulouse and two colleagues from Bordeaux. And this was funded by the European Space Agency and Total. So the question is the following: when I put two liquid phases in contact, a phase 1 and a phase 2, and when I shear it, do I see something special at the interface? So it's relatively well known that there are some slips between a liquid or a gas and a solid structure, but it's not widely studied when you are dealing with fluid-fluid interfaces. So what we have done is simply to do molecular dynamic simulation of two immiscible fluids and put them under shear. So here is a figure of the system. So there is a phase 1 and a phase 2, two liquid in contact, an interface between the two. And here is a velocity profile when you shear. So you have a linear response in phase 1 and phase 2, which means that you have something which is Newtonian in terms of viscosity. And if you look at what is going on at the interface, there is a kind of velocity jump at the interface. And indeed, if we made the two fluids more immiscible, we increase this velocity jump. It's relatively well known when you are dealing with a thermal field. It's called the thermal resistance. But when you are dealing with momentum propagation, it's not that well studied. So it means that if you are trying to simulate a system with two liquid phase that you are sharing and with an interface, there is a small slip between the two phases. And indeed, locally, you can define a kind of interfacial viscosity just by deducing the shear rate from the slip length and the width of the interface. And from this interfacial viscosity, it is clear that you can relate it to the interfacial tension. So you can define relatively easily a kind of interfacial viscosity, which is simply related to the interfacial tension. And this interfacial viscosity decreases with the interfacial tension. To give you an idea on what could be the impact of such a slip between two, or of such interfacial viscosity, if you consider a water-wet nanopore of 10 nanometer containing oil and water, the oil relative permeability is roughly 2 times bigger when you take into account this interfacial viscosity. We are now trying to study similar problems with the inclusion of surfactants, and it's more problematic because it leads to Marangoni effect, so migration of fluids due to interfacial tension gradient. Now I will move to an additional problem, which is I have dealt with two-phase situation in a nano-confined environment. Now I will deal with multi-component dynamics in a complex system. To tackle that, we have made some simulation of a mass transfer through a complex amorphous matrix, carbon matrix. It's mimicking a kind of kerogen, even if it's only a rough representation. And when you are dealing with such system, you may ask yourself some question. For instance, could you have a molecular sieving effect, so which will lead to separation of different species from a gas or a liquid when crossing such a porous structure? May you see selective adsorption? How do you define the transport? Is it a collective or a single mass transport? And indeed, you can, we have done some work on that, especially in kerosene with some colleagues, Patrick Bonneau, Amel Obligé, and Romain Vermoil from the lab, and Julien Collel from Total. And you have probably seen things which are similar during the talk of Professor Chin. And what we have done is the following. So again, it's simply simulating a gas system, a gas mixture composed of methane or CO2 and pure fluids as well at such temperature in reservoir condition, and to look at the response of the flow relatively to the external force. So if you look at how the fluid transfer or transport itself from this part to this part, you can define a flux, and you can relate that to a pressure gradient, something which is often done in the oil and gas industry, where they employ what they call the Darcy model, so where there is a linear link between the flux and the pressure gradient. If you do that, what you see immediately is that there is not a linear relationship between the two. And the second point, which is more annoying, is that if you change your fluid, if you go from methane to CO2, you change your relation. So it seems, and if it is like if the apparent permeability is dependent both on pressure and temperature and the molar fraction, which would mean that it's not a Darcian flow. But indeed, it's simply because the force that is used to determine the relation between the flux and the force is not the correct one. So you should not express your relation in terms of flux versus pressure gradient, but use a chemical potential gradient. And what counts is simply the chemical potential gradient. And if you do that, you have a simple linear relationship between the flux and the chemical potential gradient. To go beyond that, what we have looked after is whether or not it is a collective transport or a self-transport. To do that, we have simply done some simulation comparing the self-diffusion, the black symbol, with the collective diffusion for different loading. And as you can see, they both match with each other, which means that because of the small size of the pore, indeed, the fluid behaves as a self-moving fluid. So simply the self-diffusion is sufficient to characterize the diffusivity, the diffusion in such configuration. You can even go further, but I will not detail that, to determine a master curve in terms of transport, meaning that in such system, knowing just one mass diffusion coefficient helps you to define the transport for any kind of hydrocarbons. Still, there are some open questions about that. And the first one is probably, and the main one is probably the fact that we have assumed in this simulation that the solid matrix is rigid, which is not the case. And so taking it into account, the swelling of the matrix leads to another story. And this is something that is done by Christina Eskina with Amel Obligé now. So now I will move on to the second part, which is related to the big scale, the reservoir scale. So the idea is just to show you that in some situations, this small scale simulation can be useful as well at the reservoir scale. I have taken, again, 3 different examples. The first one, which is how we could coarse grain the fluid model to make it, for instance, compatible with Saft-like equation of state. And this is something that has been done by some colleagues from the lab with Jean-Luc Daridon and a colleague from a Applied Mathematics lab. And this is, as you will see, a strategy which is very similar to the one that Eric Muller shown you some week ago. So the idea is simply, is it possible to define a coarse-grained molecular model which is adequate for the oil and gas industry in terms of fluid properties? So you have 2 options. You can describe your fluid using a very detailed molecular model. It works. It's not that easy to handle in some cases, but it may work. It means a dozen of parameters. Sometimes are not parameters, but some are not parameters, but it's a large number of degrees of freedom, and which leads to typically days of computation, hours to days. Or you can employ a very simple representation, a rough representation using this coarse-grained representation, where you have only, in our case, 4 parameters, because we have used Mi chain fluid, so a fully flexible chain composed of Mi segments, so Mi interaction potential. So you have one energy scale, epsilon, one size, one length, sigma, n, which is the number of segments, and lambda, which is the amplitude of the repulsion. And to parameterize this model, we have adopted a top-down strategy, a kind of extended corresponding state strategy, where we take a critical temperature for the energy, a liquid density for the size, the acidic factor, and one viscosity to determine the length and the repulsion. So it's possible to have a one-to-one relationship between these 4 properties and a molecular or coarse-grained representation of a given species. The question is always, what about the accuracy? And when you are using such a representation, here are some results in terms of phase equilibria, temperature versus density of different simple fluids, hydrocarbons and polluent, and here is the liquid viscosity. Overall, what you can see is that the results are good, not perfect, but good. Typically, deviation on critical pressure are about 5%, and on liquid density, 0.5%. And it works as well for interfacial tension, diffusion. And for such simple systems, the mixture properties are equally good. And you gain typically 1 order of magnitude in terms of simulation. Still, if you are dealing with long chain, you have trouble because you have a fully flexible representation of the chain, which is not compatible with a good representation of liquid viscosity. And it's obvious that it's more difficult to deal with typically a polar system, and even worse with a hydrogen bonding system. And so now we are trying to include the internal rigidity on such a chain or Lennard-Jones chain representation. If I move on how we could apply that, we have applied this approach to deal with a mixture of CO2 and heptane, not far from the CO2 critical point, to mimic some conditions sometimes encountered when you are trying to produce oil, or even look at specific oil, like in Brazil, in the pre-salt from Brazil, where you have some CO2 to push your oil, which is in place through this enhanced recovery strategy. And to look to this problem, we have done experiments and simulation with this mid-chain coarse-grained representation. So to look on why it is an interesting mixture, here is the density versus molar fraction of CO2. So in this CO2 heptane mixture, the symbols, different symbols represent experiment, and open symbol, this molecular simulation tool at this high pressure. And you see that the things are simple. Even if you assume an ideal mixing, everything is correct. So it's relatively simple. But if you decrease the pressure and you go towards the pressure which is above the critical point, not close to, but not far from to, what you see is the following one. You have an increase of density with the molar fraction, and then a strong decrease when you add more CO2. So you have indeed a strong non-ideal behavior with such a simple system when you are not far from the critical point. And to better understand what is going on, this is a topic that has been studied maybe 30 years ago by de Benedetti. We have looked about what is going on in terms of structure. So the blue sphere corresponds to heptane, and the small things which is around it are CO2. And indeed, what we have seen is that you have a kind of clustering around the normal heptane, which means that when you put some heptane in a pure CO2 system at that condition, all CO2 tends to cluster around the heptane, which leads to a strong increase of the density with a small amount of heptane. So from a thermodynamic point of view, it's relatively funny because it means that you have a strong non-ideality nearly at infinite dilution. And this small scale simulation can help you to better understand what is going on. Another topic that could be dealt with this molecular simulation is to help the analysis, the interpretation of the result coming from geochemistry. And for that purpose, we have worked on the elemental fraction of noble gases, and you will see that the things are not always complex. And this is work done with Steele Hai, Wang, Anne Batani from our lab, and Magali Pujol from Total. So the question is the following. Noble gases are often used as tracers. And if you look at their relative content, so the fractionation when they move underground, you may better understand how fluids are migrated, the origin of the fluid, how you could better understand how the fluid moves when you are storing CO2, etc., etc. And the good point is that noble gases are chemically inert and they are ubiquitous. So which means that you can find them everywhere. You have a lot of isotopes and they are fractionated, so partially separated by physical phenomena only. Furthermore, for someone that is doing molecular simulation, they are the perfect guys. Huh? Spheres, simple to model, so really good to deal with. And so the fractionation could be due to two phenomena, thermodynamic fractionation or kinetic fractionation related to mass diffusion, because they will move at different pace in terms of elemental fractionation or isotope fractionation. But the problem is that it's relatively difficult to measure their mass diffusion coefficient in terms of under georesource reservoir condition, subsurface condition, and there is so a lack of data. And you will see even the models are quite questionable. So if you are working in this community of noble gas geochemistry, people are often using this model to describe the fractionation by mass diffusion. So you have fractionation by mass diffusion because two species, two isotopes or two elements will move with a different velocity because their mass diffusion coefficient depend on their mass and on their size, as you will see, as we will see later. So in this community, people are often using a Graham's law, which means that they assume that the fractionation or the mass diffusion is proportional to the square root or the inverse of the square root of the mass. But indeed, such a relation should hold only in the free molecular regime. When you are dealing with georesource condition, you are more in a situation where you are between the kinetic theory domain, so dense gas, and the liquid domain where the Stokes-Einstein law holds. So it's quite surprising that people are using such a rule and apply it to conditions which are not consistent with a priori the theory. And so what we have done is simply to compute the self-diffusion because they are tracers of noble gases in different fluids. And here is what we have obtained. So here it's a noble gas self-diffusion in methane. And here is a noble gas self-diffusion in hexane at that temperature, at that pressure. And what we have looked is the ratio between the self-diffusion coefficient of one noble gases relatively normalized by the one of argon. And so the full symbol corresponds to the simulation and the open symbol to some correlation that you could employ like the Wilke-Chang correlation. So the first point is if you draw that ratio versus the inverse of the square root of the mass of the component, what you see is that it seems that the fractionation or the evolution of self-diffusion with the mass follow more or less the square root relationship, which is the Graham's law. It was a bit surprising at the beginning because it seems that it holds whatever you are dealing with, a gas, a dense gas or liquid phase, and it works as well in water. So it was surprising for us. But indeed, this could be relatively well explained by the fact that when you are dealing with noble gases, there is a strong link between the mass and the size. And more precisely, the inverse of the square of the size of the radius of the noble gases scale with the inverse of the square root of the mass. So indeed, such a rule holds well because what matters is the size, and the kinetic theory tells you that what will count is the section, so the square, the size, so the diameter, the radius at power 2. Still, it means that such a simple rule is valid only for the noble gases because they have this relationship between them, but it's not valid for different systems, different traces. And the last example is the one related to the study of an initial state of a reservoir, and more precisely to study the impact of thermal diffusion, thermodiffusion, Sorey effect. This is something done with some colleagues from François Montel that was previously in Total and now is among us, Henri Bataillet, Velisa Velovic from Imperial College London, a colleague from Université Paris Sud, a colleague from China, from the CAS, and another colleague from RIPED from China. And here are some figures because some of our experiments were going in the microgravity experiment, and one using the SG10 launch in China 4 years ago to get some data. So the issue are the following. It's if you want to have a good description of the initial state of a reservoir, you must know well the fluid distribution, so the compositional gradient vertically and eventually laterally. But the problem is that to get that, you need to have sampling. So, and it costs a lot to have some samples. So the point is it possible starting from the information at one point to reconstruct the fluid distribution vertically, just knowing the composition at this point, the thermodynamic condition, and having a good model. So what shape the fluid distribution? So the composition within the phases, mostly gravity through segregation and thermal diffusions, because there is a geothermal gradient, because when you go into the ground, each 3 kilometers, the temperature increase by 100 degrees Celsius. But the problem is, it's not that difficult to include segregation, but it's more difficult to include thermodiffusion, which is sometimes called Sorey effect, which is the fact that when you put a thermal gradient on a binary mixture, even without any gravity, so even without convection, you induce a fluid separation. But there is a lack of data, and you will see models are questionable. So the question is, okay, how could our nano size molecular simulation could help in modeling a fluid reservoir, which is typically of 100 meters. So how could we mimic a fluid column corresponding to 100 meters with simulation of about something like 10 nanometers? The response is relatively simple. If you have a linear response of your system under a gravity field and under a thermal gradient, then it's done. The upscaling is direct. And indeed, if you look at the 10 nanometer fluid, it could be one phase or two phase, and you just employ gravity and thermal gradient, which are 10 at the power 10 times the one in real situation. And if the linear response still holds, then you have a way to mimic a 100-meter fluid column. Typically, this is what we have done. And in the situation where you can have analytical solution, which is only validated on ideal mixture, so isotopic mixture, we have shown that this is possible because you still have a linear response, even with this huge gravity and this huge thermal gradient. And so we have studied a real reservoir. We have studied many, but I just show one example, which is a gas reservoir containing a lot of CO2 at such condition with a large verticality, 1.6 kilometer. And here I show you the distribution, so the mole fraction versus depth of methane and CO2. The symbol corresponds to the molecular simulation. Open symbol corresponds to simulation with gravity only. And the gray symbol to a simulation with gravity plus the thermal diffusion, so the thermal gradient. And the full line or dotted line corresponds to equation of state, cubic equation of state in that case. And in this case, cubic equation of state plus data coming from the molecular simulation to obtain the thermal diffusion factor. So what you see is the following. First, if you consider only gravity, you have an enrichment of methane at the top of the column. But when you switch on the thermal gradient, this enrichment is strongly reduced. Second point, you see that if you adjust your equation of state, you have a good agreement between molecular simulation and equation of state. Now, if you look at the CO2 distribution in space, when you have gravity only, you have a strong enrichment of CO2 at the bottom of the fluid column. But if you switch on the thermal gradient, so the thermal diffusion effect, you obtain a concentration gradient which is strongly reduced. So which means that because of the thermal gradient and because of thermal diffusion, you have a reduction, a strong reduction of the CO2 and the methane gradient. But even more interesting is to look at the density with depth. If you have gravity only, you have an increase of the density with depth, not surprising, huh? Because of the gravity itself, so the density will increase with depth, so as the pressure. But now, if you switch on the thermal gradient, you obtain that result, which means that you have a density gradient which is inverted, more dense at the top than at the bottom. So this is due to both the effect of thermal diffusion, which tends to push the CO2 towards the top of the fluid column, plus the thermal expansion. So which means that in that precise case, the situation is unstable because you have a density which is higher at the top than at the bottom of the fluid column. And that is why in such field, the composition of the reservoir was nearly homogeneous all over the width, all over the height of the reservoir. So it's interesting to show that even with this small scale simulation, you can even better understand what is going on at a macroscopic scale in some specific situation. So if I make a kind of a brief summary of what I have tried to show you, I hope that I was able to convince you that with this molecular simulation tool, you can have access to information which are really inaccessible by experiment, and which can help as well to better understand how to improve your modeling, especially at the continuum approaches. So it's really a good way, I think, to help further developing model. And the good point is that such tool is and force field is immediately applicable for a lot of systems, but not all. I have not discussed at all about hydrogen bonding system, or even polar ones, slightly polar ones. And it could be as well used to enhance and sometimes to check some physical or macro-physical concept. But one should always keep in mind that these simulations are based on molecular models. The results are exact for a given force field, and which all these molecular models possess intrinsic limitation. And the upscaling is not always easy, especially when you are dealing with a heterogeneous system. So just a very last example, we have tried to simulate both with molecular dynamics and CFD simulation, the moving line in a quet diphasic quet. And here is the result at the 2 scale. And what you see immediately is that qualitatively you can get it right, but quantitatively it's always difficult to be very, very accurate. With that, I want to thank all the collaborators, so the PhDs that are working hard on the topics we're trying to tackle now. Some colleagues, the postdoc, and especially Hai Wang, who has done much or most of this simulation, of the simulation that I've shown you. Romain, Amel, Jean-Luc in the lab, and as well the colleagues from Total, even if now François is among us at the university, Magali and Julien, and as well Stéphanie, Dominique, Abdul, Anne, and you for your attention, and I will be happy to try to answer to your question if you have any. Thank you.
Thank you so much, Professor Galliero, for this excellent presentation. We are now open for questions, so if you have any, please feel free to enable your microphone and ask, or if you would rather prefer, you can write it down in the chat so we can read it. Our YouTube viewers can also ask questions, of course. So who wants to be the first?
Arthur.
You can go ahead.
Okay, so Guillaume, very nice, excellent presentation.
Thank you.
I would like to ask, do you have any familiarity with Martini force field for this kind of calculations? Have you tried Martini in some of the coarse grain simulations?
No, I did not try, but I know a bit on them, yes. They do suffer from the same deficiencies than our coarse grain representation. So it's mostly the way you introduce the internal degrees of freedom. If you are dealing with bulk system and not too big beast, it's relatively fine. But when you are dealing with not homogeneous system, so for instance, on a solid structure, so when there is an organization, so when you go from 3D to 2D representation, it's another story. Yeah. And for thermal property, there is a problem because you have a so small number of internal degrees of freedom that you cannot capture everything.
Correct. We have used Martini to predict some properties in confined media related to gas to liquid processes. We didn't look very much on thermal properties, but we look at density and some phase behavior, and it was in relatively good agreement with atomistic simulations. But,
okay.
Yeah.
Interesting. But
anyway.
I think that it's if your solid structure is not too structured, it could be okay.
It was graphene. It was graphene and graphene oxide.
Okay. So it's good. Huh? It's I think it's a good choice. The Martini. Yeah.
One more question. Can you comment? You showed some results and you compared to an equation of state. Which equation of state did you use?
I don't remember exactly, but I don't think that.
Was it Eric Miller's? Was it the Eric Miller shaft gamma mi or something like this?
Alors, we have done some simulation because we were initially at the starting point of the shaft gamma mi because Thomas Lafitte has done his PhD among us.
Yes.
And indeed, it's relatively consistent with the simulations themselves, except close to the critical point because of this mean field approach. So when you compare directly with the simulation, you have an offset of the critical temperature clearly. But in that case, the comparison was done with NIST or Wagner-like equation of state, just to have it very accurate because it was on pure fluid only.
Thank you.
Thank you for your question, Yanis.
Professor Haja, I think you can ask your questions if you want.
Definitely. Thank you, Professor. I have some clarification on your comments. One is, can you estimate permeability with solubility and diffusivity alone? You hardly talked about solubility of gases in the liquids at nanoscale.
Yes, it's possible to to obtain solubility, but the problem is that you have a lower limit. So for instance, when I was dealing with noble gases, if you look at the solubility of noble gases into water, it's small. And so which means that as we are simulating a finite number of molecules, you cannot go below a certain threshold in terms of solubility. So because you have only a finite number of molecules. So if you have a solubility which corresponds to something which is lower than 10 minus 6, for instance, then you have a problem because you to simulate it properly in terms of molecular simulation, molecular dynamics, you cannot capture that. But otherwise, it's a good test, the solubility of the force field. But it's possible, yes, to get it. And in terms of permeability, it's possible, but only for a very tight structure. So it's typically for nano Darcy system. The size of the system is always small, so you cannot simulate a system with, I would say, I don't know, above micro Darcy. It's difficult to achieve.
There is another question also. Which is important, solubility effects through surface tension variation or the diffusivity? Diffusivity doesn't seem to increase very much with the temperature, but solubility may not decrease that much, may go up very much.
Indeed, it's a product of the two, so it's a kind of availability. So what counts is the product of the mass diffusion by the solubility. And it's often employed as well in the membrane community, because if you have a strong diffusivity but a small solubility, you will not transfer much. And if you have a high solubility and a small diffusivity, you will neither transfer much. So what counts is really the product of the solubility by the diffusivity. It's some type called permeance. It depends on the community. So, and you are right, both evolves in different way, typically with temperature and with pressure as well.
And the last clarification, you talked about the importance of estimating surface tension at high pressures for such systems, especially in a small scale. There is a classic method of Tolman, Lawrence, a long time ago, how to calculate the surface tension using the simple Tolman equation, the Tolman length. Do you think it's still valid, or you really have to go through your potential molecular simulations to have some corrections like that?
There was some excellent work on the Tolman length by, for instance, the group of Jackson, but not only, maybe Ioannis has worked on that as well. I don't know exactly, but maybe Keith as well. Indeed, the Tolman length is usually relatively small. So the correction to the classical macroscopic representation of the interfacial tension or the Laplace pressure exists, but it's very small if you are dealing only with van der Waals fluid. If you are dealing with fluid with charges, it's a bit different. But it's possible to check directly that the Tolman length exists by just looking at the pressure difference, for instance, in a bubble between inside the bubble and outside the bubble, and the interfacial tension that you could compare on a flat surface. And again, the Tolman length exists, but it's very, very small. So often negligible indeed.
Do you think there's a difference between droplets and bubbles in this case? For example, the curvature, negative delta P or positive delta P, is there a direction or some anisotropy in this? You talked about droplets.
Yes. I did not show that, but indeed, when you are dealing, we have done some work on the dynamic of a droplet on the surface. But the problem is that the first is difficult to define a pressure because the pressure is anisotropic itself because of the interface. And so you are right. There is a strong anisotropy in pressure, which leads to interfacial tension. But even close to a solid wall, there is as well a strong anisotropy. So if you want to have this macroscopic concept in such situation, it's difficult because your stress tensor is on the diagonal. The value may be different because of the interfaces and the inhomogeneities. So we reach a kind of limit when you are trying to interpret or trying to make a connection between the mechanical interpretation of such phenomena and the thermodynamic one. It's even difficult to define locally what is a stress.
Oh, thank you so much. It's so nice to hear you after a long time from meeting you near the race course in your city. Thank you, Professor.
Welcome.
Anyone else have a question? You can go, Professor Fred.
A nice talk. I have several questions, but I'm going to concentrate in two. You calculate some viscosity in confined fluids, and you talking about DFT. It was a dynamic DFT that you used, or you use the DFT for structure, calculate the structure of the fluid in confinement?
So I was not talking about the dynamic DFT, and my point is simply that you can employ a strategy which is similar to a DFT to define the variation of viscosity with space. So when you have a DFT or even a DGT, you just say that the energy at one point is not exactly equal to the energy of the bulk, but it depends as well to the gradient of the density locally and even the higher order. In that case, what we are doing is simply to say that we have a non-local contribution. So which means that locally, if you define, for instance, I am here, I have a given density, a given temperature. I can, if I have a correlation, deduce the local viscosity from the local value of the density. If I do that, I obtain the black line, which is not correct. So I need to assume a certain length over which I make an average of the density. And in that way, I introduce a strategy which is similar to a DFT. You can employ a Tarazona-like metric. It's not really important, but qualitatively, you can employ a strategy for local viscosity, which is similar to what you employ to determine the local density.
No, I got it. Thank you.
Okay.
I was confused about this. Okay.
It was fast.
Okay. And the other point is about reservoir grading, the last part of the talk. I didn't understand much how you deal with the gravity field. It's not clear to me. And also, as I understood, you input the temperature gradient for your system. Yeah? It's huge temperature gradient. And I'm wondering about the simulation, if you see some drift in energy when you impose this, because normally what you do is you impose some energy flux to get the temperature gradient instead of put the gradient of temperature because of the drift. I don't know if you saw that drift in energy, and also how you deal with phase transition in this size.
Okay, so many questions in one. So the first one, to apply gravity, it's simply you apply a body force. So it's I just apply a body force, which is a 10 at a point 10 times the one of real gravity. And so you can mimic kind of extra gravity just to have the upscaling between 10 nanometer and 100 meter. And it works. Huh? You can look at the problem of sedimentation and density distribution in a gravity field. It works well. In terms of temperature gradient, you are perfectly right. If we impose a temperature gradient, depending on the strategy we employed, applying a temperature difference or a flux of energy, or even a swapping of different energy, so like the Florian-Müller-Plateau, you may have some drift, with time, but this drift is relatively small, especially if you employ the reverse non-equilibrium molecular dynamics strategy of Florian Müller-Platte, and even better if you employ the modified scheme by Dan Frankel recently. And indeed, it's for our case, we didn't have seen a large energy drift when doing the things carefully. But keep in mind that we are doing a B-periodic system. So it means that here I have shown only half of the simulation box, because to keep on the periodicity, I just hit from here and cool here, but I have another box here, which is a symmetric one, so as to keep the periodic boundary condition. And last, regarding interfaces, here the upscaling does not work. Why? Because if I have a liquid gas, I have at the molecular scale an interface that may span over, I don't know, 1 nanometer, okay? It's small, but it's 1 nanometer. Then if I multiply by 10 at this 1 nanometer, but by 10 at the power 10, then I have a diffuse interface, which is huge compared to the real one. So when you are dealing with interfaces, it's fine to understand what is going on across interfaces, but the upscaling in that case is not direct.
Thank you. That I expect.
Any other questions, anyone?
Yes, I have a follow-up question. Niels Hansen from Stuttgart here. Also on the topic of the temperature gradient, the linear response, is it an assumption or was it shown that you, and theoretically shown that you can assume it?
Alors, it's difficult to show it theoretically. It's not that easy. You do even have a community that is called maybe you know that, the extended irreversible thermodynamics community, that assumes that you may have a gradient of a gradient that may appear, so non-linear response. But indeed, if you assume that from this simulation you can measure locally the temperature, what you can do is applying a temperature gradient, look at the response, which looks linear, and then take a subsample of this non-equilibrium simulation and look if this subsample, if you do simulation on this subsample, is consistent with equilibrium, and it is. So which means that even the gradient, if the gradients are huge, locally you are close to equilibrium, and so the response remains linear. Mm-hmm. The non-linearity comes only from the fact that the thermal conductivity may depend with the temperature, but not because of the relation.
Mm-hmm. Okay, thanks.
More questions?
Arthur has a question.
Go ahead, Heza.
Yes. Hello. Thank you, Professor, for your interesting presentation. Is it possible
Heza, can you open your camera?
Professor, I'm using my
no
mobile phone.
Okay, no problem. Go ahead.
Is it possible to explain about a velocity jump in interface of fluid?
Yes, I think that qualitatively it could be explained like that, but quantitatively it's not exact. Some colleagues from the group of Matar has tried to do that in that way with a dynamic DFT as well recently. So the point is simply the following one, I think, to understand that story. Yes. So here is, oops. Okay. So here is the case where you have this liquid-liquid system, so diphasic. So you have an interface. So here is the velocity in the first phase, in the second phase, and you have this jump, or at least this discontinuity, or nearly discontinuity. And indeed, it's simply because when you put two liquids which are not miscible with each other, you have a density dip between the two. So here it's the density of the two phases. You see? You have locally a decrease of density because they don't like each other. So you have a decrease locally. It's small, huh? It's over something like 3 or 4 molecular size, but there is a decrease of density. And so if you have a decrease of density, it seems logical to have a decrease of the viscosity in that region. So again, you have a kind of local viscosity, which is depending on the local density. It's not exactly the local density that counts, because there are non-local effects, like in the case we discussed with Fred, but still, I think qualitatively it's the explanation. So because the two fluids are not matching with each other, you have a kind of decrease of density locally. So the momentum will not propagate perfectly from one phase to another. So locally, you have a lower viscosity at the interface compared to the bulk viscosities. Was I clear?
Yes. You know, in interface, at the interface, capillary pressure is 0. Have you considered this matter or no? PC, capillary pressure.
Yes, here I am in a situation where it's only fluid and the interface is flat. Huh? So there is no difference in terms of pressure because I have two films of liquid connected to each other. So I don't have any capillary pressure in that case. I don't have pressure difference between the two systems, the two phases. I'm not in the confined situation. Huh? Here it's only one liquid and a second liquid. So it's two films of liquid connected to each other.
Okay, thank you. I said you have considered in the reservoir, but you have considered for two fluids in it flat.
Yes, in the reservoir it's even more complex because there is a curvature, and so there is as you said, a difference in pressure, so capillary pressure that may play a role as well. Yes.
Thank you very much for your interesting presentation.
Thank you. You're welcome.
Professor Richard Elliott, go ahead.
Sorry, I was muted. So I have a question about this slide. First, just to get oriented, it's unusual for two different fluids to have exactly the same density and viscosity, isn't it? But that's what this picture is showing.
Yeah, you are right. It's simply because I have made this phase 1 and phase 2 are exactly composed of the same fluid, and I have made them non-miscible just by reducing the cross energies between the two fluids.
Okay. Okay, that's okay.
It's simply to better see the problem, better see the effect, because the slopes are exactly the same, so you enhance and you see it more easily.
Yeah, all right, I guess, yeah, and then the result of making it more realistic is easy to expect, right?
Yeah, we have done it as well with the surfactant, and at this scale, you may have a slip between the two phases. The slip is not big, it's some nanometer, but it exists even in more realistic system.
Well, that's what I wanted to ask, was the real question after what got oriented. So the surfactant is going to broaden the interface, right? And it should decrease the density difference, right?
Yeah.
And so is there, but then at the same time, I think of the surfactant as more acting like a lubricant, right? Maybe I'm wrong about that. And so you should get more slip if it's a slipperier interface. So looking at this picture, there should be basically no difference between the phases if you add surfactant.
Yes, you are right. But the problem becomes slightly more tricky because if you want to describe it like that, you need to define nearly 3 different phases. So a kind of phase 1, which is a bulk, phase 2, which is composed mostly of the surfactant, and phase 3. But you are right, the density difference is decreased or even reduced to 0. But still, you may have slip because you have a kind, yes, you can say a lubrication. No, it's something that we are working on, but I do agree, it's qualitatively it's the same picture, but quantitatively it's different, and the way to model it is probably slightly different.
Well, I guess if it's a third phase, if you think of it that way, and it's mostly surfactant, then it's going to be the viscosity of the surfactant.
Yeah.
Okay. Interesting. Okay, thank you.
Any more questions? Go ahead, Professor Haja. Professor Haja, do you want to ask a clarification?
Can you hear me now?
Yes. Go ahead.
Some comments about Stokes-Einstein relationship, applicability to nanoscale. You talked about local viscosity and local diffusivity. And you said better to use local diffusivity in nanoscale or at least in coarse-grained scale. Can you still use Stokes-Einstein relationship to estimate local viscosity or not?
You can. In most cases, it works relatively well. Sometimes you have to play with the numbers in terms of what is it, a stick or a slip value. So if you take 4 or 6 at the denominator, but yes, globally the Stokes-Einstein applies well. It's even really surprising because you are at this molecular scale and even dealing with simple molecules, it holds relatively well. It breaks down when you are in supercooled region, but globally the Stokes-Einstein relation in sufficiently dense system holds reasonably well.
And the final clarification is about, you mentioned very briefly about Marangoni effect and variation of surface flow. How important it is, or you can simply neglect it?
In that case, in that case, you don't have any problem because you don't have any concentration gradient. But when you put surfactant, for instance, at the interface, as we were discussing previously, then if you have a small gradient of the surfactant, then you have a flow. And this flow is well described by a Marangoni macroscopic flow. So you just have to estimate the interfacial gradient, interfacial tension gradient. And there is a linear relationship between the velocity of the interface and this interfacial tension gradient. So, which means that when you don't have anything at the interface, it's okay. But when you put a third component, then it moves.
The last question is about the cavitation. Do you have to worry about the pressure of cavitation, or we can simply say there is no cavitation, or fix the cavitation pressure at some, say, 20 megapascal or something like that? Do you believe there is cavitation?
It's not. I don't. If the term, I don't know if the term believing is exactly the right term, but yes, there was. I did not work a lot on the cavitation, but we have done some work. It's possible to look at the cavitation, and it follows relatively well a Rayleigh-Plesset behavior. But the problem is that, and you can really obtain a really high pressure, huge pressure locally, for sure. But again, if you have a nano bubble, and if it implodes, then again you come back to the problem of defining correctly a pressure in such a small system, because it's no longer isotropic. The dynamic is really fast, but there's a lot of paper showing that cavitation could be studied with this kind of tool. And if you do it properly, you could model it with a Rayleigh-Plesset macroscopic formulation if you have a pure fluid. The story is different when you have a mixture, because in addition to the pressure, the huge pressure within the bubble, you have as well a temperature gradient. And because there is a temperature gradient, which is huge, you have a phenomena which is similar to what I discussed at the end, so related to a thermal diffusion. So you have, because of this thermal gradient, you have an external force or force that change the relative motion of the different species during the implosion. So it leads to relatively complex behavior.
Okay, thank you very much, sir.
Any more questions? I actually have one. In the following slide, you calculated viscosity profile in a pore. I would like to know which methodology did you use to calculate this profile through molecular dynamics?
Usually, I simply shear the system and look to the shear rate relatively to the shear stress I impose. It's to obtain macroscopic value. If you want to deduce the property locally, so to measure viscosity locally, you need to employ the microscopic formulation, the Irving local microscopic formulation of the momentum flux. So you have a local value of the momentum flux, so a local value of the shear stress from the molecular motion plus the interaction, the virial term. And so you can deduce, if you know the shear rate, you can deduce a local viscosity.
Okay, I see. Thank you, Professor.
You're welcome.
So anyone else wants to ask a question? Professor Fred, you're muted.
No, I think it's time to wrap it up.
I think it's time to wrap it up. Thank you, Professor Galliero, for this amazing presentation, and thank you everyone for the discussion.